Hi, this video is a lesson on end behavior of polynomial functions. So when we're talking about polynomial functions, we're talking about functions that we can graph that are continuous from left to right. Poly meaning many terms, so it could have one term or it could have many terms. So the first thing we want to do is analyze what kind of functions we're looking at for this first set. So I'm asking you here to make observations by graphing x squared, x to the fourth, and x to the eighth. So I'm going to, in my calculator at y equals, type in x squared, then type in x to the fourth power, and x to the eighth. Well, before we even graph these, what we can notice about them is that they have two main things in common. The first is that their leading coefficient is a positive 1. Recall that a leading coefficient is the coefficient of the term with the highest degree. Well, being that we only have one term, in this case, our leading coefficient would be 1, an understood one, and because it's not negative, we know that it's a positive 1. So they all have this leading coefficient of positive 1 in common. The second thing they have in common is that their degrees, meaning their exponents, are even. 2, 4, and 8, they're all even. So let's consider that. That means that for all three of these, our a value is greater than 0. Whenever you see that, please recall that it just means greater than 0 means that it is positive. In addition to that, our degrees are even. So we'll put up here even degrees. So this is what we're considering first off. Well, when we type them in our calculator and graph them, let's see what we get. The first is a parabola. Oh, that looks like another parabola. And then another parabola. So it looks like all of them remind us of the parabola x squared. Well, the reason is because if we were to look at our table, as we input values, if we input a 0, 0 squared is 0, 0 to the fourth is 0, and 0 to the 8th power is 0. So they all have this common point, 0, 0, which is why we see it touch the origin. After that, looking at our table, when we square 1, we get 1. 1 to the fourth power is 1, and 1 to the 8th power is 1. So they all have the point 1, 1 in common. Do you see what other point they have in common? Oh, they have negative 1, 1 in common. Negative 1, 1. Negative 1, 1. So all of three of these would have at least 3 points in common. However, after 1, when we raise 2 to the second power, we get 4. If we raise 2 to the fourth power, meaning 2 times 2 times 2 times 2, we get 16. And 2 to the 8th power would mean 2 times itself 8 times, we get 256. So what this means is that as our exponent gets larger, when we raise it to a power, it gets bigger quicker. So instead of being 2 squared is 4, 2 cubed is 8, we're dealing with much larger values. So what we see is our graph is vertically stretched as our exponent increases. So just think about it like if we took these two ends here and kind of pulled them upward. Wouldn't that make our graph get skinnier, or what we refer to as narrower? So what we notice is that the graphs are very similar. They have 3 points in common, 0, 0, negative 1, 1, and positive 1, 1, and that the larger the exponent gets, the narrower our graph appears. But what we do notice, however, is that they all have something else in common, and that is that both ends go in the upward direction. So what that means is that for all functions where our a value is positive and our degree is even, we're always going to have both ends go up. So if we were to consider the graph of y equals, let's say, x to the 6th power minus 2x to the 5th plus 3x cubed plus 4, it doesn't matter what these terms here are. If we do graph those, let me clear out what we have here. And if we type in x to the 6th, please remember that if you type in an exponent larger than 2, After the exponent, you will need to hit the right arrow to move our cursor down. So x to the 6th minus 2x to the 5th plus 3x to the 3rd plus 4. There's a couple things I know. I know that because my leading coefficient is positive, understood 1 here, right? And because my degree is even, I know my ends are going to go up and up. I also know that this positive 4 is my y-intercept. And I bet if I look at my table, I'll see the ordered pair 0, 4. Let's test that out. Second graph. Yep, there it is. Our constant term is always our y-intercept. So now that we have our function entered, let's hit graph. So sometimes we'll get all kinds of different things. Like in this case, we see, well, there's other movement to our graph. But if we consider just the ends, what we notice is they do, in fact, go up. So that means all polynomials that have a positive leading coefficient, meaning the number in front of the term with the highest degree, in this case, it was 1. And as long as our degree is even, remember that your degree is the highest exponent of a polynomial. So even though you see the exponent 6 and the exponent 5 and the exponent 3, that the degree is the largest. So our degree is 6. So because it fits this criteria, we know that both ends go up. Now let's consider what happens if given this circumstance where we have the opposite of x squared. So I'm going to go in here and type this in. This would be read as the opposite of x squared, the opposite of x to the 4th power, and the opposite of x to the 8th power. Well, when we graph these, let's see what happens. Interesting. This looks like the graph did before, only they're opening down. So what that tells us is that we can define our a value, understood 1, right? However, it's a negative. So if our a value is less than 0, and remember all numbers less than 0 are negative, so don't let this notation scare you. It just means that our a is negative. And our degree is still even. Remember, we're still dealing with even powers, squared to the 4th to the 8th. So if we have an even degree but a negative leading coefficient, that means our ends are going to go down. So I could come up with a similar function. I'll just make something up here, but make it fit this criteria. If I have negative x to the 4th power, let's do plus 3x cubed minus 2x squared. I can make up whatever I want. Plus 6x plus 1. If I type it in, I bet both of my ends of the function will go down. Let's see. Let's clear out what we have. Negative x to the 4th power plus 3x to the 3rd power minus 2x squared plus 6x plus 1. All right, let's graph it and see if we're right. Oh man, that one looks different too, but notice what happens to both ends. They both open down. So next, let's consider what happens. I'm going to fold this in half. Let's consider what happens for number 3. So if you take a look at number 3 and we make some observations, I think we'll notice something that they had in common with number 1, and that is that they had a positive leading coefficient, meaning our a value is greater than 0. Again, remember that just means it's positive. But the difference between numbers 1 and 3 now is that our exponents are odd, so we call this an odd degree polynomial function. So let's see what observations we make when we graph it this time. So if we graph x cubed, x to the 5th, and x to the 9th, let's see what we observe. It increases from left to right, increases from left to right, still increasing from left to right. So notice that we have opposite in behavior, meaning as our x values get more negative, our y values get more negative. And as our x values get more positive, our y values get more positive. So if we had to draw arrows for this one, I would say that it's down on this end and up on that end. Hopefully that helps you to see that. Now the reason is when we raise a negative number to an odd power, think about it. If we had negative 2 to the third power, that really means negative 2 times negative 2 times negative 2. Well, a negative times a negative is a positive, then a positive times a negative 2 would make it negative again. So that means every time our input value is negative, our output value will also be negative. While if our input value is positive, our output value would be positive. This is why as x goes negative, more and more negative, our y value goes more and more negative. And as our x value goes more and more positive, our y value goes more and more positive. So this would be a description of what happens here when we have a positive a value but an odd degree. For number 4 here, if we take a look at this, similar to number 2, what we should notice is that our a value is less than 0. There's an understood -1 for all of these. So again, negative leading coefficient. And again, similar to number 3, we have odd degrees. So we call that an odd degree polynomial function. So let's see what happens here. My guess is that if it goes down on the left and up on the right, then maybe similar to how it flipped the graph for 1 and 2, maybe it'll flip it here. But I'm not sure, so let's check that out. So since I already have them in here, I'm just going to insert my negatives. To do that, I'm going to hit second, and then notice right here above the delete key, it says I and S for insert. So I'm going to hit second insert, and then just hit the negative button. And when I do, I'm able to insert a negative. Second insert a negative, second insert a negative. So let's see what happens to our graph. Oh, now it's decreasing, decreasing, decreasing. So we're right. On this end, it went up on the left side of the graph and then went down on the right side of the graph. See how that makes sense? It went up on the left but down on the right. This is very important for us to understand because that helps us to define our end behavior. So I'm going to flip back up here to the top and we're going to talk about end behavior real quick. So what we need to really understand when we write end behavior is that there's a particular statement that we must write that is a mathematical statement that helps to describe what happens to the function as our x values decrease, meaning they are approaching negative infinity, and as they increase, meaning they are approaching positive infinity. So this is how we would write end behavior. So we could abbreviate end behavior EB, and there's two statements you're going to write. The nice thing is the two statements you write are going to be exactly the same, except at the very end we will fill it in according to the directions of our arrows. So this is how you write an end behavior statement. And you have to write it just like this, and this is how you say it. As x approaches infinity, f of x approaches blank. The second half, as x approaches infinity, negative infinity, f of x approaches blank. So what this means is you have to consider what would happen if, say, these were our axes, and we're trying to consider what happened as x gets larger. As x on remember our x-axis is our horizontal axis. As x gets larger and larger, we have to think, what is f of x doing? Well, remember, f of x is the graph of your function. It, in fact, is your y value. So think your y-axis is vertical. So as x goes horizontal towards positive infinity, what is happening to our y? Well, if you want, you can even label your axes each time to help you get oriented. Remember, as x gets larger, that's positive infinity. Y getting larger is towards positive. X getting smaller towards negative infinity. Y getting smaller towards negative infinity. So let's consider what happens. As our x value approaches positive infinity, so take your finger and go to the right, what is our function doing? Well, it's going up. Toward what? Toward positive infinity. And that's what we fill in the blank. Now we repeat the process, but as x approaches negative infinity. So take your finger at the origin, head left towards negative infinity on our x, and think, well, what is f of x approaching? It's going up on this end, so it approaches positive infinity again. So this means as x is going outward, the function is going up. And this is our end behavior statement. When I ask you for end behavior, this is what you should write. Moving to the next one, when a is less than 0 but with an even degree, the nice thing is, again, our end behavior statements look exactly the same. Our job is to simply fill in the ends. So you need to write this over and over to practice it and get the hang of it. As x approaches infinity, f of x approaches blank. As x approaches negative infinity, f of x approaches blank. So now you can pause it for a moment to write that down. What I'm going to do again is draw in our axes, and remember positive infinity, negative infinity, negative infinity, positive infinity up here, and repeat the process. Again, starting with my finger at the origin, as x is approaching positive infinity, what direction is our function traveling? It's going down forever. Well, down forever is towards negative infinity. As x approaches negative infinity, f of x is again going down. So it's approaching negative infinity. Just remember, this thing is going down, down, down continuously. And once you have your blanks filled in, you're all done. So moving along to this one, condition where our a value is positive but it's an odd degree. If I draw in my axis here, positive infinity, negative infinity on my x, positive infinity and negative infinity on my y, and I start to write my end behavior statement, I again repeat the statement. As x approaches infinity, f of x approaches blank. As x approaches negative infinity, f of x approaches blank. So pause it now if you need to copy that down, and then you pick back up. So again, I'm going to repeat the process. As x is going positive, my function is going up, so it's going positive. One thing that may be helpful as well is to think, well, what quadrant is this in? And since this end is in quadrant 1, which is positive, positive, note that those are the signs of your end behavior for that side. This side, it would keep going down, down to within quadrant 3, where both coordinates are negative. So if that's the case, then that means as x is approaching negative infinity, f of x is approaching negative infinity. And I'm all done. Last one. Positive infinity on the right, negative on the left. Once you get the hang of it, you won't have to write as much. So in behavior, let's see. As x approaches infinity, f of x approaches blank. As x approaches negative infinity, f of x approaches blank. So if you look here, since this end is in quadrant 2, where my signs are negative, positive, this is exactly what will help you with your signs of your end behavior. This side, since this is quadrant 4, recall quadrants 1, 2, 3, 4, y'all remember that? Positive x but a negative y. This actually will help you with your end behavior statement. So let's do the first one. As x is approaching positive, my function is going down towards the right. So that's going towards, oh, and I totally messed that up. That should have been negative infinity. It's going down forever towards negative infinity. Notice these signs. This is positive infinity. This is negative infinity. Positive infinity, negative infinity. Likewise for the last one, as x is approaching negative infinity, my function is approaching positive infinity, so these signs here apply. Negative infinity, positive infinity. So you can put the positive if it helps you. If you leave it off, it's still understood to be negative, so either way is fine. But your end behavior statements have to be written just like this, so you need to practice it, okay? So if I go back and think again, if I understand the graphs visually, do I understand how that applies to an example for a polynomial? Let's see if you can make sense of this. If I ask you to write a function to represent this, a function where both ends go up, that has a positive a value with an even degree, I would expect you to write an example such as f of x equals positive, so I could make it any number I wanted, 5x, but pick an even degree, maybe 4. And you can even do more terms if you like, but that would suffice. If I asked you to write an example for with a negative leading coefficient with an even degree, you could use the same one or create something different, but maybe negative 3x to the 6. See how that satisfies both conditions, a negative leading coefficient but an even degree, which is the exponent. Here, if I ask you to write an example, we'd want one that was positive but with an odd degree. So maybe a positive 2, x to the 7th power. That has a positive leading coefficient and an odd degree. And lastly, if our leading coefficient is negative and with an odd degree, maybe I'll make that 5, that would be an example. So this is actually, if you understand this, going to help you understand the worksheet that we did in class where we looked at different polynomials and talked about end behavior and how to write it. So I hope now that you are able to correctly write end behavior statements such as these by simply understanding the sign of your leading coefficient and the degree of your polynomial and what that means for the ends of your graph.